Hey, welcome to our last lesson of Unit 2. So you should be wrapping up this lesson, going back, reviewing the concepts, going through worksheets, finding questions that you struggled with, making sure you understand in preparation for your test for the second unit. You definitely want to be writing this test before spring break because if you don't do that, then that's really going to put us off pace for being able to get through all of our units after spring break, but before the provincial exam, with leaving some time in there to review at the end. So if you are pushing it and you're getting close to spring break, I still really encourage you to write it during spring break. If you're around over spring break and you need to make arrangements with me, I will meet you at a Starbucks or at a Tim Hortons and you can write your test over spring break. That's cool with me. I'll even treat you for coffee, but we need to get this done before coming back on April 1st for 2009 school year anyways, so that you can be on time in terms of being ready for your provincial. So that's kind of my expectations of where you're at. I would even really like you to start diving into the next unit, our third unit, before spring break, but definitely finishing the second one, because these have been two pretty beefy units, so definitely finishing 1 and 2 is important. But with that said, lesson 9. So we've got some things to consider, going back just as like a recall at the beginning, like we have had for the last couple lessons, dealing with inequalities. So take a second, pause the video to practice solving, but have a look at these inequalities. Okay, so going back to inequalities and thinking about how we have the restrictions on domains. In our first step here, we can isolate x squared, and then we would want to take the square root of both sides, and remembering that when we introduce a square root, it can be both positive and negative. Okay, so I had the option of positive and negative 4, but then I need to consider, okay, well, this is talking about a parabola, right? And so we need to be dealing with, where is it like greater than or less than 16? Okay, so bearing that in mind, or greater than or less than negative 16, where is this happening? So we kind of can check some points or logic it out. So if x squared is less than or equal to 16, then that's going to be looking at when I have to be dealing with numbers smaller than or equal to 4, because if I went to up to 5, then I would have to be dealing with like 25 over here, and that doesn't really work. So you can logic it out, you can actually check values, and that's what I did in the second one. So here, I couldn't just isolate x by moving my constants over onto the other side, so I had to actually factor and break it apart. So we had two options. We have x is greater than negative 3 or x is greater than 2. So in that case, only one of those can really be true. So I had to actually check it out. And when I plug in negative 2, which would satisfy this inequality, I still resulted in this equaling 0, which is not okay because it had to be greater than 0. It could not be equal to. But when I check positive 3, which is bigger than 2 here, and I plug that in, that satisfies my inequality. So I'm going to work with that particular restriction. So graphing composite functions. So example 1, graph f of x and g of x. So we'll start by just graphing each of them individually. So x, or f, and g. Okay, so f, we've got, if I wanted to like rewrite this in terms of like helping me with transformations, sorry, I'll go back into orange. I would rewrite this as negative x minus 3, in which case my b value is negative, so that's going to reflect it, and my c value is going to be shifting it to positive 3. So now that I know those pieces of information, I can roughly sketch what my curve is going to look like. Oops. So, here we go. So again, reflected over the, sorry, I did that incorrectly. Reflected over the y-axis and shifted by 3 to the positive side. So this should be where we're looking. There we go. Okay, so that is f of x. G of x, I'm dealing with a parabola that's shifted down 1. That's a lot easier to draw and wrap your head around. Okay, so parabola shifted down 1, still opening upward. Okay, so there we go. Okay, so domain of f of x. Well, that would be x is an element of the reals. I'm going to use set notation this time just because I have been shying away from it lately. And x has to be less than or equal to 3. Okay. We also have our range, which is that y is an element of the reals, but y is greater than or equal to 0. For g of x, our domain is going to be any real number, so just x is an element of the reals, and range would be y is an element of the real numbers, but y has to be greater than or equal to -1. So again, you could write this in interval notation. I just figured I'd switch it up since my bias is towards interval notation. You've seen that a lot. Okay, complete a table if we're talking g of x and f of g of x. So g of x, if we go in here, -3 should be 8, 3, 0, -1, 0, 3, and 8. Okay, so then if I'm going to be plugging those values in to f of x, I'm going to go in and say, okay, well, 8 being taken away from 3 is going to get me to negative . Sorry. 8 taking away from 3 would be -5, and we can't take the square root of that. So that is not possible. Or you can just give a nil. Okay. If we plug in 3, well, 3 subtract 3 is 0, so that would give us 0. That makes sense. That's what we see here. 0, so 3 take away 0 is 3. Square root of 3 is some less than 2 value. We could even just call it the square root of 3. -1 in there, so 3 plus 1 before square root of that is 2. And we see that in -1 there. And then going back, we've got root 3, 0, and that's not permissible again. So if I go to graph this now, I've got a very restricted space in which to work. And so that becomes apparent. I'm going to do this in blue. So I've got 0, -3, and 0 now. Or non-existent. So I don't have a point there. -2 and 0, sorry. -1 and square root of 3, which would be roughly here-ish. Okay. 0 and 2. 1 and 3, 2 and 0. And so we end up with this weird, just like mini parabola that actually has a restricted domain. So I've graphed it, again labeling it f of g of x. I forgot to label g of x. Okay. So then going in and saying my domain and range, well, my domain now becomes very restricted. Sticking with my set notation, x is an element of the reals, where -2 is less than or equal to x, which is less than or equal to +2. And my range is going to be, where y is an element of the reals, but y only exists between 0 and +2. So significantly more restricted than my original function. So composite functions definitely needs to be considered like, what are my ranges? Because all of a sudden we've got like rules within rules that we need to think about. Okay, so let's try this next one. I suggest that you try doing at least the graphing of each individual function and the domain and range of both of them. So if you want to pause this video now, do that, and then we can come back together to complete the table. If you want to continue that on your own as well, feel free to give it a shot and go all the way through to the end of the example. Just remember to check your answers, make sure you're doing it correctly, and if you do get stuck, scroll back and try and find kind of like where your mistakes are, and always email. Okay, so domain and range, I did them in interval notation because I find them quicker. I've got my graphs of my two functions. I've got them labeled, f of x and g of x. I should have arrows on the ends of this line as well, just a heads up. And so now I can complete this table to start doing combining functions. So g of x at -3 is -5. Oops. And 0, 3, 4, 3, 0, -5. Okay, so then I'm going to take these and I'm going to put them in to my f of x, and I can pull the values right from the graph. So the input is -5, output's -4, 0 should be 1, 3 should be +4, +4 should be +5. I could also be getting this from using the formula. That's entirely possible as well. Okay, but since I can pull them from a graph, that makes my life a little easier. Then I start going back the other way. So 4, 1, and -4. So I can graph these points, and the nice part is here that I don't have any restrictions like I did in my previous graph. So good news, because both my domains are not restricted, that results in an unrestricted domain in my final piece. So that's a nice trend that we can expect. Unrestricted domains in both functions result in an unrestricted domain in my composite function as well. So I'm going to use black just because it shows up better than that light blue. I'm going to graph all these points. So input was -3, output's -4. And so that's a key mistake that some people make. They'll want to put this as their x value, but this is not your x value. This was your x value. We just used g of x as our input to our f of x function. But remembering that x is on the very, very inside, so that is still our input. So I go with -3, -4. -2, +1. -1, +4. 0 and 5. And then back the other way. And so again, I would expect this to kind of be parabola-esque. Again, if you need to retrace to make sure your shape is looking good, that's really, really important, making sure that curve is smooth, making sure we're going through those points. and this is going to be my composite function. Remembering also that we can write this as f of g of x. Either notation is fine. Okay, so my domain, like we said, still has no restrictions. Range, on the other hand, does have a restriction. It doesn't match any of the restrictions we had originally because now my graph maxes out at positive 5. So it's a new restriction, but still a restriction. Oops. That should be square bracket because it is a defined point. Now, looking at the graph, trying to graph f of x. So remembering that f of x is x plus 1. So input-wise, for just f of x, I'd go negative 3 plus 1 is negative 2, negative 1, 0, 1, 2, 3, 4. So then when I go to do this again, I'm putting these values in as my quote-unquote input now. I'm going to add another 1 to them. So this should be negative 1, negative 2, oops, 0, 1, 2, 3, 4, 5. Okay, so again, I'm seeing a trend where, like, if I had a quadratic in my original function, I end up having like this quadratic shape here. When I do f of x, I'm dealing with two linear equations, and that's pretty much what we're seeing in our output, and we'll see that when we graph it too. So I'm going to take negative 3 again as my input, negative 1 as my output. Negative 2 is my input, and 0 is my output, and so forth. And so this becomes my line, and so again we see that linear shape stays true because both original functions were linear. So then we go to list our domain and range for this. Well, because it's the same function within a function, we're seeing the same piece again. So negative infinity to positive infinity, unrestricted, so it stayed unrestricted. Range was unrestricted, and we see that's also maintained. Okay, so we've got example 3. Again, I would encourage you to try this one on your own, especially that first part of graphing the original function. If you want to see kind of what it might look like to graph these other two functions, I will walk you through it, but you're more than welcome to give them a shot as well before we kind of tackle the last little bit of information. Okay, so my two initial functions are g of x and f of x. We see those on the graph in those two colors. I'm going to work with a slightly darker blue. I'm not really happy with how that light blue's been working so far. So instead of making a table of values, what I'm going to do is I'm going to do what we were doing in the previous lesson. I'm going to kind of combine these functions and make a new equation. So f of g of x is going to end up being the square root of x plus 3. And when I go back to thinking about what my transformations mean, that means that I'm taking a regular square root graph and I'm shifting it left by 3 because that plus 3 is inside the function. So instead of drawing my square root graph starting at 0, I'm going to shift it left by 3. It's going to start here. I have no b value, so I haven't stretched it. There's no a value. I haven't compressed it. I haven't shifted it up or down because there's no constant outside the square root. So literally I'm going to take that same exact shape that I had previously, and I'm going to shift all those points just left by 3. So left by 3, left by 3, left by 3. So this is why I like doing this unit as part of transformations, because having that background in transformations really helps us kind of solidify how to draw these graphs once we've made our composite functions. And so this is now f of g of x. Okay, so my personal predisposition is going to always be to create the new equation and try and come up with it from there. If you liked the table of values method that we did in examples 1 and 2, by all means, you are more than welcome to keep using that as your strategy. There's nothing wrong with it. It will still be just as efficient. My only concern with doing that is, again, when we go back up here, remembering that this is still going to be your input for the actual coordinates that you're going to write in. So again, this would become -3, -1, not -2, -1, which might be something that kind of trips you up. So you're more than welcome to do it. Oop. There we go. So for my last one, I'm going to do the same thing, and I'm going to plug in f of x, the square root, into g of x. So it's going to change my equation a little bit, and now it's going to look like this. It's going to be the square root of x plus 3. So now I'm seeing that vertical shift because my plus 3 is on the outside of my function, that square root. So I'm not going to shift left. That plus 3 is not inside the function. It's not under the square root. It's on the outside, which means it's a vertical shift. So instead of horizontally going left 3, I'm going to go up 3. And so we see each of these points going up 3. Again, working from that original f of x, because that is the square root function. That's the one that's defining my shape, because it's the one with the restricted domain and range. And so there we go. So we've got our 2 combination graphs. We've got our 2 original graphs. So here are some rules that you can use. For the composition function f of g of x, the function f is applied to a range of g. The domain of f is restricted to x equals greater than 0. So f of g of x is defined when g of x is greater than 0. That is when x is greater than or equal to -3. So that might be some kind of convoluted language, but basically we're saying because we know the restriction of our function f, we can apply that to our restriction on what we can use from g of x. And if we define that, well, g of x is greater than 0 when x is greater than -3. Okay. For a composite function, when g is on the outside and f is on the inside, g is not restricted, so we only care about f. And so we see that, well, f is restricted and it's greater than 0, so g of f is going to be defined for x is greater than 0. So we don't have that shifting going on because it's our internal function that is the one that's restricted. Okay, so it all depends kind of which function is restricted and what the restrictions are that influences how does that manifest when we do a composite function. In general, if we have f of g of x is only defined for when x is some number a has to be in the domain of g, and g of a has to be in the domain of f. Okay, so these are our requirements. So going back to that very first example, because that was probably the trickiest one for seeing this, we saw that f of x was restricted to x had to be less than or equal to 3. But g of x could be bigger than, which is our new kind of like quasi input when we do a composite function. G of x didn't fit within those restrictions. So we hit that roadblock where, well, we were able to look at -3, but actually we couldn't get an output there. So within that, we had to look at, okay, well, what restrictions on g would allow us to only work with values in g that fit our restrictions on f as well. Okay, and so that's why we ended up sitting with that restriction of between -2 and +2, because our outputs in g fit the restriction of our original domain of f of x. So it's probably the most complicated piece that we're going to be learning in this unit. It's a pretty tricky thing to wrap your head around. That's why I like to default to this notation as opposed to working within those specific values on a table of values. So whenever possible, I like to default back to my transformations. So that's what I would recommend, but definitely table of values are still perfectly acceptable. And so that's what the second part of our lesson is looking at. It's determining explicit equations, or actually taking the equations and combining them. So that's what we're doing here for example 1 and 2 of this section. So when we say g of f of x, that means that this function here is going to go in place of x. Okay, that's what's happening for this one. So when I go to write this, instead of x, I'm writing 1 over x plus 3 squared minus 4 1 over x plus 3. Now, I can try and simplify this as much as I want, but the reality is I can determine my non-permissible values from here, and so that's kind of the key other piece that I'm going to be looking at. So for my domain, because g is not restricted, f is the only thing I care about. So x cannot be -3. So again, in set notation, what that would look like, it's just x can't be -3. And that's the end of the story. If I was doing this in interval notation, I would do this as -∞ to -3, which doesn't actually exist, but provides us with a kind of roadblock that we can keep going then to positive infinity afterwards. So again, keeping that idea of like, this is what a reciprocal functions domain kind of looks like, and we still see that manifesting when we do the composite function. Conversely, if we go back up here, for this second part, b, we're going to be taking this function and plugging it in place of x here. So what that looks like is we're going to go 1 over, and instead of x, we're writing x squared minus 4x plus 3. Well, no glaring non-permissible values appear here. It's a reciprocal function. I can identify that, so I know I'm going to have some non-permissibles. But what are they? Well, that comes from, again, being able to identify like what we're not allowed to put in the denominator. And that becomes easier if it's factored, if it's a quadratic in the denominator. So if I've got x minus 3 and x minus 1 as my two factors, then my non-permissible values are going to be x cannot be 3 or 1. And my domain will reflect that. So set notation, x is an element of the reals. X cannot be 1 or 3. Always listing smaller first. Or, and this is where interval notation kind of falls apart. It becomes very onerous to write. From -∞ to 1, from 1 to 3, and from 3 to positive infinity. So you might default to set notation. You could totally write this as interval. Both are acceptable, but just a heads up that it becomes more complicated with more non-permissible values. Working with these, we've got a square root. So again, x has to be greater than or equal to 0. And we've got no restrictions on our domain for g of x. So for the first one, we're going to put the square root in to where x is. So the square root of x squared minus 4. Well, that just becomes x minus 4. This is amazing because we've essentially eliminated our restrictions. That's a kind of unusual piece, but in actuality, it still does exist. We've just simplified it out of there. So our domain would still be reflected as our original f of x restriction. So x is an element of the reals, and x would be greater than or equal to 0. So if our new function does not have any restrictions, just double check that the original functions also don't. And that kind of harkens back to the idea way back in grade 11 when you had something like x minus 2, x plus 2 over x minus 2 as a reciprocal function. Although those canceled out and this function simplified to x plus 2, we still had to include that non-permissible value of the original function where x could not be positive 2. Same thing's happening here. Even though our new simplified function g of f of x doesn't look like it should have any restrictions, because f of x had that original restriction, it still needs to apply to its domain. So doing our second one, we're going to plug this into our square root. So the square root of x squared minus 4. And so this becomes a little bit trickier in terms of graphing. We know that what's underneath here cannot be negative though, so we can still solve for kind of our restrictions in our domain. So x squared minus 4 has to be greater than or equal to 0. So x squared has to be greater than or equal to 4. And that means that x has to be, in this case, outside of the square root of 4, because we need to be making a number greater than 4. So x has to be less than or equal to negative 2, or x has to be greater than or equal to positive 2. And so those are our two restrictions. So working backwards creates this set of scenarios here. So example 1, for each function where we're given y equals f of g of x. So f is the outside function and g is the inside function. Determine possible functions of f and g. So again, going back to what we had done before with these, I really strongly believe in keeping things as simple as possible. So when I look at these questions, how I approach them is I look for kind of like a bigger function and then a function within a function. So what do I mean by that? Well, when I look at this, I see that it is both a reciprocal or radical. Sorry, not radical. Yeah, reciprocal function, because I've got x in the denominator, but then within the denominator, I see a linear function. So knowing that, when I go to break this apart, the reciprocal is the bigger function. It's the one that the linear function is nested into. So given the fact that g is inside and f is outside, that's how I would assign it. So I would say f of x would actually just be the 1 over x idea, just the reciprocal. And g of x would be just that linear function, x plus 3. Now you could do all sorts of crazy things and have things canceling out and whatever you want. Like, there is no reason that you can't say that f of x is, oh, I can't even at the moment come up with a better example of what it might have been. But yeah, no, I honestly can't even see something that would be easy to come up with without getting very complicated and having to test it out thoroughly. So I would say stick with what is simple and try and break it down, break what's there into some obvious functions. And so again, we see this with b. This little square tells me that I'm dealing with a quadratic. And again, within, I'm looking at a linear function. So I would say that f is the outside, the quadratic is the outside. So I would say that should just be x squared. G of x is our inside function, so that should be x minus 2. Okay, so here I could see how this could become very like easily kind of convoluted. If you went and said like f of x equals like x minus 5 squared, and then g of x equals x plus 3. That would simplify when you plugged this in to make it x minus 2 squared. So that could work. You're more than welcome to play around with that. But again, I don't know if that's absolutely necessary when I can just pick it apart into 2 generic functions. So if you want to give it a try with C, you can pause the video now and try it yourself. I will talk through this example though, so pause it now. And if you didn't pause it, then you're sticking with me. Here, again, that second that square root sign shows up, I know I'm dealing with a radical. I'm sorry, reciprocal, another word would be rational. Okay, so radical, and within my radical, again, I'm dealing with a linear function. So radicals on the outside, so I'd say f of x equals the square root of x, and g of x equals 3 plus x. So again, the keeping things simple kind of works out in our favor here. Graphing composite functions, well, we've already played around with this a little bit. If we are given g of x is the absolute value of x, for this first one, we'd be actually rewriting this as g of f of x would become the absolute value of x squared minus 1. So we've already done this. This is not new to you. You should have done this in grade 11. So it's just taking anything that was in the negatives with my quadratic and making it positive. So if I imagined my f of x graph, and I'm going to do that in a light color. Maybe this is the one I'll do in light blue, just for the sake of drawing f of x. Well, it's just shifted down, but it's a parabola, so I'm drawing. Like this. And again, the function of an absolute value is strictly for the purpose of making anything that's negative positive. So with that in mind, everything that's above my x-axis already is positive, and so it should stay relatively the same. I shouldn't be changing it at all because, well, it's already positive. The absolute value has no impact on it. So it's just this little section down here that's going to be impacted, and there we go. Similarly, if we look at the absolute value of this function here, we've got the absolute value of x plus 4. And so if we imagined our original graph being a line, because it's linear, bear with my shaky hand as I try and draw a straight line. Pretty wavy. Imagine it straight. Again, that absolute value only starts to impact my graph when my graph becomes negative. And so I'm going to see it just go upwards instead, that reflection. But this whole side should be the same. This is already positive. And again, I should be labeling my scale on all of these. Okay. So if I was taking the absolute value of C, again, absolute value just makes everything positive. So the only part of the graph that's going to be impacted is anything that's below that x-axis. So I'm going to try and duplicate this part. Okay, but then this part is going to look something like that. And that would be my g of f of x. Okay, and finally, this last one, again, absolute values in and of themselves only affect what's below the x-axis. Anything negative becomes positive, anything positive stays positive. And so I'm just going to reflect this part up. I've got a defined point at 0 and 2, so at -2, so that'll be 0 and +2. And so I'll just try and connect my graph up that way. There we go. And then I would otherwise retrace this and call that g of f of x. So this lesson was probably the most complicated one of our last 4. It really is just a matter of getting comfortable with the idea of composite functions, a function within another function, and recognizing that because a domain has restrictions, when we put it into a composite function, that is going to impact the domain of our composite function. So always before you start working with composite functions, if you're going to have to be looking at graphing, looking at writing equations, make sure you're identifying the restrictions in the domains of your original functions so that you can kind of watch out for that once you've written your composite function as well. Otherwise, if you have any questions, please ask. There is an assignment posted for this lesson along with our previous 4 or 3 lessons. So make sure you give that a shot. And again, you want to be writing your test before spring break for this unit.